continue from where we left last time. So what were we doing? We were looking at this axiomatic system for arithmetic and then proving a bunch of theorems. We have a bunch of them listed out over here. These were a bunch of theorems that we were proving. And Levi proved the last theorem, theorem 10, which was that distribution works across subtraction just like it does addition. So that's what we ended off with. And I told you guys I'd let you just finish proving these out rather than having you watch me do it. Sound good? You changing your mind on me?
I'm not changing my mind.
You're not changing your mind. All right, so theorem 11. I'll try and make it make sense to you and then let you go from there. Theorem 11. So it's for all x, if x is not equal to 0. For all x, if x is not equal to 0, I'll do square bracket there, then there must exist some y. Is that a unique y?
Yeah.
This is our uniqueness proof.
Yep.
Then there exists a unique y such that x times y is equal to 1. So that's what we're proving. Note that this is very similar to something we already proved.
Theorem 5.
Theorem 5, we proved that for every x, there's one and only y that you can add to it to get 0. Let's say that in more grown-up language. What's the grown-up way of saying that? For every x, there's a unique additive inverse. There's a unique number you can add to it to get the additive identity. This is saying for every x that's not 0, there's a unique multiplicative inverse. There's a unique y I can multiply by to get multiplicative identity. Right? Okay, so that's what you're trying to prove. Who wants to do it?
I'm trying to remember how we did the last one. We did it by...
You want me to do this one and then you do the next one?
No.
Wanna? All right, then let's go.
Go ahead.
Let's all stare at each other.
Just have to step up and just take responsibility. Goodness. Okay, so I would start by proving that one exists, and then I would...
We're already guaranteed one exists by this axiom. Right here.
Okay,
So axiom 9 tells us that there is one.
so I can
Our job is to prove it's unique.
immediately assume by way of contradiction that 2 exists, or that more than 1 exists.
Yeah, that's why we're getting through this. We're already guaranteed one exists. So if it wasn't the case that there was only one, then that would mean that there's 2 or more. So we're going to assume that there are 2 or more and show that leads to an impossible worldview. Therefore, there's only one. The contradiction of there not being only one is there's more than one. We're going to show that's impossible. So there must be only
Oh,
one.
wait a minute. No, that's too early. I need to let...
And remember that that fancy R is our symbol for our domain over here, instead of all real numbers. So he's grabbing a random real number, calling it x, and he's going to show that for any random x he chose, there's a unique y. As long as x wasn't 0, you might want to put that in your top line. Let x in R such that x is not 0. So he's assuming he has some x that satisfies the antecedent. Oh, I missed my implication. If x is not equal to 0, that implies there's a unique y. Sorry. Probably don't say anything.
Paying attention.
Yeah. We're just not fluent enough.
To catch something like that right off the bat.
Nah, Emma must not be here.
Yeah, she would have caught that. Is she
Okay.
not going to be here this week?
Not today. Not today. Maybe later this week. I don't know.
Okay, so now I make my assumption.
Oh, sure. So we know that there is some y in R such that x times y equals 1. We're guaranteed that from axiom 9 over here. He's going to assume by way of contradiction that there's some other thing in R. Not sure what he called it.
Z.
So he's going to assume that there exists something else in R, he's calling it z, such that x times z is equal to 1, but z is something different from 1.
Yep. Z is not equal to 1.
Yeah, so z is not equal to y, but z is also a number such that x times z equals 1.
Okay. Okay, now.
So now we're going to get a contradiction, which is going to be that y is equal to z.
Yeah.
Don't you try and make x times z equal to y times z? Just substituting it in, because you know they're both equal to 1.
Yes.
Yes. Now he sees how to do it from there.
Okay. Oh.
Sounds like you should approve this one.
Yeah, Peter, geez.
Maybe.
I could only read this stuff. I can't write it.
Can I jump straight to this step, or am I skipping something?
Then x times
No.
z is equal to y times
X
z.
times y.
Sorry, x times y is equal to y times z. No, x
No.
times z. Sorry.
X times y is equal to x times z.
Hey.
Okay.
Yep.
And then, which, was it a theorem, or was it,
Yeah.
which theorem was it?
You're looking for your left-hand cancellation law?
Yeah, for multiplication.
I don't know if we ever did that for multiplication.
Is that what this basically will be then?
Oh no, we got it.
Have we done that one yet?
14.
No, we haven't.
We haven't done that one.
Oh, we haven't done that one.
That's tricky.
Well, isn't that annoying?
So we did
We
the wrong
could do
way.
a little llama. Do it off to the side.
You can still do it without that.
How would
It's
you
just
do it
we're gonna
without
have
it?
to go
then?
to the same logic
That's
of
what we
it.
have to figure out.
Do you have to like break it down to its?
You would probably do it the same way that you would prove that, but in a specific case. Would be my guess.
I don't know how you would prove that one.
Well,
It's gonna be similar to how you prove that, yeah. You're gonna have to use similar logic. It's not a huge stretch.
Are you gonna have to use theorem 7, or I mean axiom 7?
Axiom 7. Yes.
Okay.
x times 1 equals x. Oh, so we're gonna
I
have to
don't know.
multiply it by something we call 1, right?
I don't know if you have to use it. I see a way to do it.
I think they see it the same way.
Because ultimately,
So-
you're trying to show that y is equal to z. That's your contradiction.
So we multiply everything by 1, and 1 turns out to be,
Oh, and then you substitute it. Well, then what do you do from there?
okay, but what is 1 equal to?
Well, let's start with what. Here's how I go about thinking about it. I start with y. Y equals what? And I keep messing with it until I got y equal to z.
That's a good point.
So that is my intuition for how to go about doing this.
Why?
Rather
Well,
than
the way
starting
that you
with,
So-
do that is by dividing both sides by x, right?
But you
it's
can't
left-hand
you can't do
cancellation.
that.
I mean,
So use axiom
We
7,
don't
but
have
instead
notion.
of x, use y. Y times 1 is equal to y.
Y is equal to y times 1. Okay, that starts us.
okay.
And then you would
Or, let's see,
Let me
plug
get
in
it
the
off to
y.
the side here.
y is equal to, I do 1 times y. I think that's gonna make it easier for you.
Which is equal
I guess
to
everything's
what?
commutative and associative, so that'll be easy enough.
Which is
either
equal
way.
to x times z times y. Is that right? Well, that doesn't.
You can do that substitution if you want.
It's not how I was.
I don't think that's the right
See
way.
how that helps us.
I was
reading
plugging,
all this.
I was gonna plug in y for 1 times y.
What's another, look, you know y is equal to 1 times y.
Yeah, and then you can plug in
And
the
you
one.
know that if you get what two terms together, you can use them. You know how to mess with an x times y.
this one.
right? Yeah, well, you have something for x times y. You know you can mess with this. You can substitute with this. You can do things with this. Right now you just have a y. I want to get an x in there somehow. Here's one way to do it. Okay, that looks like it's going to chase us in circles.
Yeah.
What's the other thing I could put there? And it's still true.
X times y, right?
You can do the y if you want to.
X times
You
1.
can't do x times 1.
I guess
X
you can go
times
straight
0.
to z.
X times 0.
Maybe stick with what you're thinking.
You could do
I
x-
see maybe how you can keep going with this. Okay, so you got to here. Okay. Okay.
Were you trying to go for x times 0? Is that what you were trying to? No,
No.
because that would be the whole thing. The whole thing 0.
No, doesn't matter. So y is equal to 1 times y, which is equal to 1 times y. Okay.
Okay.
Now we want to get the z by itself. We want y to be equal to
So
z.
use associativity.
Oh, okay.
Oh. Okay. I think I see it. So then x times. Wait a minute.
I just start with y equals.
Oh yeah. Okay. Equals 1 times y. Equals x times z times y.
It would have been better to put the 1 at the end. I don't know if you want to fix it on the fly or keep going.
Why does it matter?
Doesn't.
Commutativity, associativity.
Keep going.
This is equal to x times y times z.
Okay, you kind of did a lot there.
I did associativity and commutativity at the same step.
You did associativity, commutativity, associativity.
Yeah.
Okay.
You want me to break it down?
Well,
I can do
it
it.
just needs to be clear how we're justifying that.
Okay.
We just need to make sure that we're not relying too heavily on our intuition for how this stuff works, and we understand how it falls from the axioms.
So just be rigorous.
Well, I wouldn't even require you to write out all the steps. If you would just said out loud, and it would have been clear.
Trying to get
He worried me because he just said associativity and commutativity,
x times z.
which I think just meant, yeah, the notion is that you could do that using those, but I
You
didn't
just
know,
went
like, the
right
saw.
back to your first step.
Oh,
You want to
whoops.
change the y and the z.
I went to flip those around. Oops. Okay.
So associativity, okay,
X times y times z
yes.
equals x times y times z
Good.
equals 1 times z
Wonderful.
equals z. Ta-da!
Contradiction. We got x, y is equal to z when y is not equal to z. Therefore, I just say no such z exists or something.
Can I do that? Is that okay?
Therefore, there exists a unique y in R such that x times y equals 1. But yeah, sure.
Actually, I'm a little confused how 1 can become x times z.
Assume by way of contradiction that there exists some z in R such that x times z equals 1. So we assumed that there was some other number out there, z, such that x times z equals 1. We showed that that was impossible.
Oh.
But it was by assumption that x times z equaled 1.
Okay.
Yeah, kind of a dead spot on the whiteboard.
Yeah, it's hard
To see.
Right, so.
Yeah, I know what I mean by dead spots.
We need to repaint the board and what it looks like.
Just get a whole new one.
Is it just paint?
There's a special type of paint that you can put on it that's basically chalk.
Oh.
It creates like a
I
really
don't know if
rough
you've seen like
surface.
those DIY projects where people will paint along their house and it becomes a chalkboard.
No.
They exist.
Huh.
That's
Cool.
pretty cool.
Yeah, we need to do something. This is terrible. It's either that or dead
You
markers.
just have to compare it some way. I don't know exactly how to do it.
Yeah, probably needs to cover down real well. Okay, so that was theorem 11. Now let's move on to theorem 12. Theorem 12 says that for all x, the multiplicative inverse. Oh, we need definition next. So now we get our new definition. Our next definition
Want me to just read it to you?
is that, I think I'll be good. For all x, y, and z, x times y equals z. Oops, x divided by y is what we're defining. Actually, yeah, did I do x divided by y or y divided by x?
I don't know which one you're looking at.
But you have x inverse there. What are you looking at?
Oh,
It's
that's not the definition the author gives. Sorry. We're getting, that needs to be proven as a theorem. Definition the author gives is x divided by y is equal to z is logically equivalent to x is equal to y times z.
Yeah.
And notice that this is almost identical to how we define subtraction. Did I write the author's version of subtraction here? Yes, I did.
Okay.
And then I proved the common sense one as a definition. So the author says, for all x, y, and z, x minus y equals z if and only if x is equal to y plus z. So we define subtraction in terms of addition. Now, we're doing the same thing here. We're defining division in terms of multiplication.
That's where y is not equal to 0, right?
Thank you. So sometimes one way we can write that is we put as an implication, I could have said for all y where y is not equal to 0, then for all x and for all z, blah, 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 blah. When we want to do this, I could have, instead of writing it this way, I could have said for all x where x is not 0, this is the case.
Yeah.
So I'm going to show you that notation here. For all x, y, and z, where y is not equal to 0, then x divided by y is equal to z if and only if x is equal to y times z. So that's the definition the author gives for division. Then we will prove as a theorem. Oh, sorry, I am skipping way ahead. We're not defining division. We're defining the multiplicative inverse.
Okay.
The
so
same
now
way
I know
that we
what you're
defined the
looking
additive
It's on the
inverse.
other side.
Oh my goodness.
That's my.
Oh. Yeah,
Inverse.
it's right there.
Wow, skipping way ahead. Okay, so this is similar to when we defined negative numbers. Definition. Negative x is equal to y if and only if x plus y equals 0. That's what we meant by negative x. Definition. X inverse is equal to y if and only if x times y equals 1.
Right.
Okay. So, write the definition over here. For all x and y, where x is not equal to 0, x inverse is equal to y if and only if x times y is equal to 1. Okay, now makes more sense. We're introducing a definition now for the thing that Levi just defined, or just proved. Levi proved that for every x, there exists one and only one y, such that x times y equals 1. We're going to call that unique y. Since it's one and only one thing, we can now name it. We can now define it.
Okay,
We couldn't define it if there were multiple things that satisfied it.
Right.
If you said, give me a definition for who Levi is, and I says he's a person in room 5, that doesn't define Levi. There's 4 of us in here. If beforehand I proved that there's one and only one person in room 5, then it's now safe to define that person and name him. We can now name that one and only thing. So what is x inverse? It is the one and only number you can multiply by x to get 1, provided x was not 0.
Right.
Okay.
Okay, so now we're proving that the multiplicative inverse of the multiplicative inverse gets us back where we started, right?
Theorem 12, yeah. Up on the
Theorem
top.
12. Okay. And this is going to be similar to Theorem 6. Theorem 6, we proved negative x is the same as x. Now we're going to prove Theorem, I forgot, 12?
Yeah.
We're going to prove that for all x, the multiplicative inverse of the multiplicative inverse is just equal to that number itself. Alright.
I mean, I didn't watch you guys do the other one, but I did want to do this one.
That's weird. I recorded it and uploaded it just for you. I
See if it blows
started
up.
out the lecture with a special dedication to Peter.
Oh, that's nice of you. It's not an implication.
Let x in R.
Yeah, we need to grab a random real number and prove that it is the multiplicative inverse of its multiplicative inverse.
Let x and r, just let x and r, right?
Yeah.
Such that x is not equal to 0.
Thank you.
I think I was supposed to put that up there. I didn't write it over here. But for all x where
Yeah,
x
you
is
did.
not equal to 0, x inverse inverse is equal to x.
So
I
then,
wrote the theorem wrong. I should have said for all x, comma, x not equal to 0. I have it written down over here too.
oh, okay.
I have theorem 13 written right. I should have done this. For all x where x is equal to 0,
Is it?
da, da, da. For all x where x is equal to 0, da, da, da.
Don't we have a definition for 0 to the negative 1?
No. That's the whole
No,
point.
no,
0
no,
to the
point.
negative
That's
1
division
is
by 0.
undefined.
That's division by 0. Okay. Okay, sorry. Thinking of 0 to the every other power is 1, right?
0 to every other power.
Is 0. Everything to the power of 0 is 1.
0 to any power except 0 is 0.
Yes.
0 to the 0 is often called 1. If you plugged into your calculator, it would probably say 1.
How does that work?
Whoa. Is this the
Uh,
dead spot you're talking about?
Yeah.
Yeah, that's awful.
There's
So-
some justification for it. Anything to the power of 0 is equal to 1. Any real number to the power of 0 is equal to 1.
Right.
There's some justification for it. I don't
Because
like
0
that they
is
call
one.
0 to the 0 1.
Isn't that
And there's arguments
basically-
against it.
seems related to infinite forms somehow?
If you take the limit of x to the x,
As x approaches 0.
as x approaches 0, you get 1. And if you take it from the left-hand side, you also get 1. So you'd be tempted to say, okay, so 1 makes perfect sense.
Yeah.
The problem is if you take it from the left-hand side, you're introducing complex numbers.
Why?
Because what is negative 1 to the 1/2?
It's a complex number.
Yeah, that's 1 over I.
Yeah.
Right. And so you're introducing complex numbers. So if you really want to define it, you need to make sure that the limit as you approach, not just in any real direction, but any complex direction is also 1, which it's not. And you can get other numbers. So some people say, because they say, well, if you just approach it from the right and left on the real numbers, then you get 1.
So when you're working with real numbers, it doesn't really create any problems.
You can't really take the limit from the left, only working with real numbers though. Because then you get a negative to negative. You get negative 1. Oh, sorry, this was supposed to be negative 1 to negative 1/2. You would get negative 1/2 to negative 1/2, as an example.
Right.
Which, what is that? It's a complex number.
Yeah.
So, if you were plugging into your calculator, plug into Google, 0 to the power of 0, I would guess it would most likely say 1. But, if you ask someone who had a PhD in mathematics, is 0 to 0 1, they probably say no, and people shouldn't be doing that because
That is undefined or 1.
I don't think I'm doing this right.
Alright, let's see what we got.
So, I chose a number and let that equal x to the -1.
We can just use x to the -1 now. We now know exactly what x to the -1 is. The same way that we know what negative x is.
So I don't need to go through all this.
So you don't need to relabel it z. You can
Okay.
just use now x to the -1 directly. So let x in R such that it's not equal to 0. So now we know it has a multiplicative inverse. So we
Okay.
can just use it.
So x to the -1, right? That's where I want to start.
I would start with x and show it's equal to x to -1. But you can start with that. It's identical in my thinking. X to the -1 to the -1.
Would be equal to x to the -1 times,
Would be equal to itself times 1.
yeah. Yeah.
Self times 1?
Yeah, so it's equal to x to the -1.
I'm trying to follow the definition.
We don't need to use that definition now.
Oh, why not? Isn't that the point of...
So that definition tells us now, what does that definition tell us? That tells us anything times its multiplicative inverse is equal to 1.
Exactly.
So we can use that fact now.
Oh. So x to the negative... Oh, I see what you're saying now. I get you. X to the -1 is equal to...
X to the -1 to the
to
-1.
Times
the -1.
No,
x to the -1.
you're missing -1 here. The inverse is not the same as the inverse of the inverse.
Oh, thank you. Times, that's what I meant. Is equal to 1.
Okay, we do know that.
Okay. I don't need to use the definition at all in this?
You're using the definition. You just used it only 2.
Yeah, you're right.
Now you're gonna
What
say
else
I need to look at what you
one
guys...
is equal to something.
Yeah,
Just
keep
like
looking at
all
yours.
those.
You already did the hard part.
That's the easy part.
What else is equal to 1?
X times x inverse.
Okay.
Alright.
And I just substitute?
No. Yeah, you need separate stuff, but yeah. You have to just pop them together, they're equal to each other.
Okay.
Now you have to use the cancellation law again. It would have been so nice to just prove. the
Yeah, we
cancellation.
should just prove that first, huh?
I probably should have wrote it the other way.
Yeah.
Can I do that?
Creativity.
Just community. Yeah.
You're setting those equal to each other?
Yeah, because they're both equal to 1.
Okay, let's see where you're going.
You're right. I mean, I can write it out a bit more.
No, you're fine.
No,
Just
then
keep
you
going.
just-
I'm
you
just
cancel out
not sure
the
where you're going.
X inverse.
Yeah, I do exactly what Levi did.
How do you cancel it off?
How did you do it? I don't
You have to
remember.
multiply it by 1 or something.
No, it was...
We used.
Well,
Axioms
you're
of-
already got that fact that you're using.
Yeah, we use Axiom 7. Thank you, that's what I needed. We know that x inverse times 1 is equal to x inverse.
Okay.
And substitute that in.
Wait a minute.
I would start
Go ahead
with
and circle.
x inverse times 1.
Why? I guess we'll see where we go.
Because you're going to prove that you're ultimately trying to show this is equal to this.
Yeah,
So either start with this and keep messing with it till it looks like this, or start with this and keep messing with it till it looks like this. And obviously the way you're messing with it is you're multiplying it by 1.
okay.
I don't care where you start,
So step 4 might have been unnecessary.
but the only thing I wouldn't do is
Well, that helps me
start
think
with
about it a
x
little bit more.
inverse.
Okay, so then I can just,
Now 1 is equal to.
1 is equal to x times x inverse.
Okay. You're gonna want x inverse.
Oh, yes, thank you.
14, we probably should just prove it. We'll do that next, since it's so easy to prove.
I actually don't know how to prove that, so it'd be nice to see.
Okay? You
Now
don't
you're
laugh
just
when
gonna
I show it
use
to you.
commutativity to associativity till the x inverses cancel.
I have 3 x inverses.
That's not right.
Yeah.
What did you do?
What did I do?
Which one did you want to multiply by?
You're
two
one-
ones.
I took this, I plugged in 1 with this.
Okay, this should
Maybe plug
This
in
is
one
not
with
right.
a different one.
That is right.
Maybe plug it in with a different one.
Oh.
Plug in with this one.
See what happens.
Okay. That's what I thought to do.
Because when it cancels, you'll
Alright.
get x out.
Oh, because you want to get x.
Yeah.
That's
Yes.
obvious. Okay. Can I just implies here?
Sure.
Okay. I want to get these two.
Using commutativity and associativity.
Yeah, but Levi did that, so I don't feel bad about writing that.
So much for rigor.
And this is equal to.
You group together the.
Oh, I grouped together the wrong things. That's what I meant to do. Then we have 1 times x equal to. I know I'm skipping some steps, but I think you guys can follow me.
You get the idea. Alright, it's left as an exercise.
Okay. Wonderful. Let's just write that just a little bit different, just for the fun of it. Okay.
This is what I got used to doing calculus.
So x is equal to x times 1 is equal to x times 1 right?
Yeah.
Put those two together.
Yeah.
What? Okay, that's my support.
And then this is 1, so you're left with just that.
So half of our proof there was kind of unnecessary.
Yeah. Well, that was unnecessary thinking then. Okay. And now, since we keep running into this, I'll quickly prove theorem 14, since it's such a tough one.
Oh, come on.
Don't want you guys to get too stuck. This one says, for all x, y, and z, where x is not equal to 0, right?
Yeah.
Yeah.
Prove that if x times y is equal to x times z, then y is equal to z, right?
Pretty much.
Alright.
That's the opposite
Fine.
cancellation of what's there, but either way.
Let x, y, and z in R such that x is not equal to 0. And we're also assuming that x times y is equal to x times z. Right?
Yep.
2. Then, multiplying both sides by the same thing we can always do. So then, x inverse times y is equal to x inverse times x times z.
Oh wow, that was so easy.
I'm a little lost. How you got there? Sorry.
So I know x times y is equal to x times z,
Yeah?
and I can multiply both sides by the same thing.
Oh.
Using
You
just,
guys proved that before?
that's a theorem of logic.
Oh.
Theorem of logic, for any operator, if A is equal to B, then for any operator, as long as the symbols we're talking about are defined using this operator, then A operator C is equal to B operator C.
Okay.
For any operator.
And also.
How do we prove that? We substitute in and replace B with A. And obviously everything's identical with itself, and we can substitute equals for equals.
Oh yeah.
So it's just using our two rules for how you work with identity. So that's theorem of logic.
Okay.
Make sense?
Yeah, now I follow.
All right, this is theorem 14. So that's equal to that. It would have been like that. Obviously use associativity to group those two together, and then that becomes a 1, that becomes a 1, we get y equals z.
Yep.
See how it follows from there?
Yep.
Okay, so there, now we have that. So we can stop getting stuck on that.
Okay.
All right. And now we'll go back up to theorem 13 and prove whatever that is.
Negative x inverse is equal to negative x inverse.
Ah, cool. For all x where x is not 0. So this is a cool one. For all x where x is not equal to 0, the additive inverse of the multiplicative inverse is the same thing as the multiplicative inverse of the additive inverse.
Okay.
Okay.
Make sense?
Yeah.
All right.
Is that back to me or?
Sure.
I would have to make my hand help the whole way through if I was to do it.
That's what we're doing.
Try it if you want.
Might as well learn how to write it.
Okay.
For all x, and x is not equal to 0, negative x. What is this term called again?
That's inverse.
The
We can
inverse
prove
of
that
x.
that's inverse.
Which I understand it is just simply 1 divided by x, essentially.
It turns out that's the case. But
Okay.
it's just a symbol for the thing, such that when you multiply by x, you get 1.
Right. Okay.
So you would start assuming the entity.
There's no antecedent, it's no implication.
Well, you have to not
You just
antecedent,
say
you have to
let
say
x
let
be a
x.
real number, such that x is not 0.
Yeah.
Oh, yeah, right. Okay. I know how to do this. It's,
The weird E symbol.
yeah,
Yeah.
and then it's like a R.
Or 2 lines, yep.
Yep, okay. And then, such that x not equal to 0.
Okay.
And then, okay, so, okay,
So would it be easier to start with the left or the right?
That's a good question. I don't know. My gut says the left, but I don't have any good reason for it. Negative x inverse.
I guess it's the right.
I'd rewrite the negative as a -1 times x inverse. Ooh, now we'll get in trouble with that. So yeah, if we start with the right,
Then you could say.
we're going to do
definition
negative
inverse.
x
Yeah, we could
inverse
use the
times
definition probably.
negative x.
So you could say there was a number.
which one are we looking at?
We're looking at theorem 13. Looking at this.
No, I know that we're looking at that, I'm saying, what one are you guys looking at to break it down?
We're
The
wondering,
definition, right above it.
we're wondering, should we start with this and make it look like that, or should we start with that and make it look like this? Because we gotta show that this is equal to this, or this is equal to this.
Right.
So we're gonna start with one and manipulate it
Until
until
it
we
equals
spit
the
the
other
other
one.
one out. And so we're guessing that it's gonna be easier to start with this one and mess with it until we get the other one to pop out. So we know
Sorry, I
that
didn't reach out to you yet.
negative x inverse, if we multiply by 1, we don't change it.
Are you gonna see if he's there? Just wait, worry about it.
You said you called me.
Okay. I don't want him calling us at night. Where are you guys?
Oh, well, starts to begin.
Okay.
So you would use the definition somehow, somewhere. But where?
See, when I did, I started with negative x inverse, okay, so I did start with that.
Would it make sense that we would be, if we inverse the inverse, it would make it x, and that would like,
But we have two different inverses, so let's see. I'd start with this left-hand side. So
Okay.
let's start with this.
Okay.
And then we're gonna multiply by 1. So that is equal to itself times 1. So all that is equal to, now we're gonna do a substitution for this 1. We want to do a substitution for this 1 that uses this symbol. How could I rewrite 1 with this symbol in it? This is the multiplicative inverse of what number?
x.
Negative x.
Yeah, right, negative.
It is the multiplicative
Yeah,
inverse of
negative
negative
x
x.
times
If
negative x.
if you had to say in words what this number is, it is a number such that when you multiply by negative x, you get 1. It's negative x's multiplicative inverse.
Right.
When I say what is A inverse, it is the one and only number such that A times A inverse is equal to 1.
Yeah. and it's-
Okay, so we don't have A inverse, we have negative X inverse. What is negative X inverse? It is the one and only number such that negative X times it equals 1.
Great, so that's one way to break it down. And okay, I see what you're saying.
Okay.
So are you saying that you would essentially be able to make this say that x negative 1 times negative x, I'm just gonna do that. Like that?
Right, so now we know that's equal to that.
Okay.
Now, what do we want? We're trying to get this term by itself. Right?
Mm-hmm. Oh yeah, you're right.
So I somehow need these two things to combine together to be 1. So if these two things are somehow just 1, then we got this by itself and we're good.
Right.
Well,
That does make sense.
The negative of the negative is just a positive, right?
I don't know where you're getting a negative of a negative.
You would switch the two terms,
You'd
the
say
middle term and the far left term.
negative
The
1
middle
times
term and the far left term, you're saying swap those two.
Yeah, and then you have
negative x.
negative x, exactly.
So the moment I'm
He's
looking
saying
at it like this.
negative is negative 1.
Right, and he's doing a lot there.
Yeah.
This is not, this is a unary operator on that symbol.
But they're being multiplied, so
It's
you
a
can
sub-
just combine the two, right?
Subtraction.
Well, you need to have arguments for that. I can't have
Oh.
something like negative 7 plus 4 and just go ahead and swap the 4 and the 7 around and say that's the same thing as negative 4 plus 7.
But can you do that with multiplication?
Maybe justify it. It turns out you can with multiplication, but that has to be
Have we
justified.
not proved that yet?
Yeah.
I don't know. Let's look
Oh.
at the theorem.
It's the corollary right there. Under theorem 8.
Negative 0 is equals 0.
That's what we want to use.
Yeah, this is what we would want to use. That wasn't doing what Peter said.
No, it's not, but that's what we want to use.
So this one says the negative of a number times the negative of a number is equal to the products without the negatives.
Which is what you
Oh, so you can just do that on the two far right terms?
Yeah.
Okay.
The two
Well, the left.
These
left
two?
terms. No.
Oh, these two.
Remember,
Yes,
we
sorry,
don't want to
that's
mess
what I
with
meant.
this one. This is what we want to be there when it's all said and done.
Right.
So it's better to think about your parentheses going
So-
around.
I mean,
Those
those
things.
around.
Yes,
like
that.
is 1.
X inverse times x. That makes sense.
Am I able to pull this right out? Is there a theorem we figured out for that?
Yeah, so look at what this one says. This says if you have a negative some number and times negative some number, then that's equal to their products without the negatives, which is what you have here. You have negative some number times negative some number.
Oh, so, I see. So it's more like, okay. Alright, it's making more sense here. Okay, so so this symbol and that symbol, so in that case, I could say that this is now equal to, x negative 1 and, times x
Yeah.
Uh-huh.
times, My
They
what?
don't cancel.
Well, they equal 1.
Your two left-hand terms,
Oh yeah, they cancel out to 1. You're right.
they cancel out to 1.
Okay. So that would just be 1 times x 1.
Which is exactly what you want.
And we prove that this is equal, that times that is equal to this.
Ta-da.
Right. We have proved that. That's one of our axioms. Anything times 1 is just
Yeah,
like
that was a
thing.
lot easier than I thought.
Yeah, that is.
These things tend to-
So yeah.
they tend to be-
So you showed negative
We just
x
took over
inverse
the
is equal to
place.
the inverse of negative x.
That's badass. Okay.
Sure, you did a lot worse in real analysis.
Alright.
And then all that just like goes down the drain.
Now we do our next definition. Our definition for division now. Okay. Before we do our definition for division, let's go back and talk about some numbers now. So when we were talking about R, and we were saying, what do we know is in this set? What do we know is in the set? We knew that 0 was in the set, and we knew that 1 was in the set. Those were our two undefined terms in the set, based on our axioms.
We knew that the integers were in the set.
Well, then we knew that 2 was in the set. We defined 2 to be 1 plus 1.
Here.
And we had then definitions for 3 and for 4, dot, 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 right?
The natural inverse.
The naturals. And then we did a proof, or we defined what a negative number was. We defined what a negative number was. And so that gave us, oh, there also must also be negative 1 in here, negative 2 in here, negative 3 in here. Right? And so far we didn't have fractions.
They find the inverse.
The inverse now gives us fractions. We are guaranteed that there must be some number in R such that when I multiply 5 by it, I get 1. There has to be something I can plug in here such that I get 1.
Right.
And so we call that number 1/5. And that's the definition of 1/5. It's the multiplicative inverse of 5.
Okay.
And so that's how we get 1/5 and 2/5 and 3/5 and 4/5 and 5/5.
What's that set called again?
Rationals.
It's not the rationals.
It's Q.
The rationals is all the
Yeah,
fractions.
yeah. Oh, that's right.
Yeah.
Q. That's what I was looking
So this is how we're now able to start defining all our fractions. And then once I have 1/5 as a fraction, I'm guaranteed for any two real numbers, when I add them together, it's another real number.
Yep.
And so 2/5 has to be a real number. And 3/5, and da 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 da. And now we can come up with definitions now for all our fractions, in terms of the symbols we have.
for. Oh, and that's what we are doing in this new definition, right?
Well, this new definition, we're now defining fractions.
Okay.
Right? So I meant this not 1 divided by 5. I didn't mean this as 1 divided by 5. I meant this as a fraction 1/5.
Which is the same.
Okay.
The same way that negative and minus are very closely related. The multiplicative inverse, I mean, I could have written this as 5 minus 1 instead. Maybe that would have been better. And then we could prove that 5 minus 1 is equal to 1 divided by 5 once we have divided by defined. Maybe that
Are we
would
going
be
to do
better.
that proof?
We can.
I would like to see that.
Getting ahead of ourselves a little bit. So
Okay.
let's first do what we have as our next definition. So now our next definition introduces division. And so definition. Do I divide by y or x?
Divide
Why?
by y.
So for all x, y, and z, where y is not equal to 0, we say x divided by y is equal to z is logically equivalent to
Oh.
Yeah, we
X
just did right zero.
is equal to y times z.
Yeah. Yep.
Right?
Yeah.
Now, a much better definition would be x divided by y just means x times y's multiplicative inverse.
Yeah.
Much more precise. So we're going to prove that as a theorem. We're going to show that this gives us this.
Okay.
So
That's
our
the
next
theorem.
theorem, what number is it?
15.
theorem 15
Yeah, that
is that for all x and y, where y is not equal to 0, then x divided by y is equal to x times y inverse.
Yep.
So that's our next proof. All right.
See what we can come up with.
Obviously, we have to use the definition.
Yes, we're gonna have to use a definition.
Would you just use it at the first?
Yeah.
Just use z and then show that z equals to x times y inverse?
Yes.
Okay.
Yeah, you show z is equal to both halves of that equation. Oh my goodness. Sorry. Oh, is that how it's defined then?
Yeah.
Yeah, that's exactly.
Okay, I didn't change anything. Okay.
In that definition, you just forgot to put a z. The one on the whiteboard.
The one on the whiteboard.
When you said for all x, y.
I see. Yes. All right. Let x, y, and z be real numbers such that y is not equal to 0, and x divided by y equals z.
Oh yeah. Thank you. Okay, now, so my end goal is to get that z is equal to x times y inverse, right?
Mm-hmm.
So I need to figure out how to get a y inverse in there.
You have to play with that first part.
Maybe use this.
Use your definition. You know x divided by y
What's that?
equals z. What does that tell you?
Tells you that x is equal to y times z.
Okay.
Which theorem? Do I need a theorem? We're trying to basically get.
Oh, multiply each side by y inverse.
Yes.
There you go.
Yeah.
Okay.
Okay.
Here we go.
Want to see it? You just gotta yell.
Yeah.
Sorry.
Yeah, that was easy. That was the step I missed in my brain. Okay. Y inverse times x is equal to z. Oh, I forgot to use whole sentences there. But that's life. Okay. Therefore, what was I getting at here?
Remember, you x equals something, or z equals something.
Wait a minute. Make use substitution, right?
Yeah, what did you make z equal to?
Wait a minute. Wait a minute. I'm getting it, okay? Oh, now we use the same definition right here, right? So oh. That shouldn't have been that hard.
Alright.
Okay.
So then y inverse times x is equal to x divided by y, or x divided by y is equal to x times y inverse. And so this is a far more common way to define division than the way the author has here. And so most people will say division is really just multiplication. What does it mean to divide by y? It means to multiply by y's multiplicative inverse.
Yeah.
So when I take 4 and I divide it by 2, what does that mean? That means 4 times 2's multiplicative inverse, which is 1/2.
Right.
So dividing by 2 is the same thing as multiplying by 1/2.
Okay.
Cool.
So all division is really just multiplication. The same way that all subtraction is really just addition. What do I mean by x minus y? We meant x plus negative y. That's what we meant.
Right.
Similarly, x divided by y is x times y's multiplicative inverse. Okay. X theorem.
Well, now we're dealing with inequalities.
Oh no, that means it's going to be hard.
No.
Oh, you'll see.
Yes.
For all x and y, if x is less than y,
No, they're just specific.
theorem 16.
Inequalities of any.
For all x and y, if x is less than y,
Take the class.
then negative y is less than negative x. Let's give a concrete example. If 3 is less than 10, then that means negative 10 is less than negative 3. That's what it's
You
saying.
have, oh, yeah, okay.
As a concrete example.
Mm-hmm.
All right. Give you the first step, assume the antecedent.
Okay.
Step 2, show it implies a conclusion.
Wow.
And you're done. 2-step proof.
It's so easy to
What do you mean?
All right.
It's like every proof I've ever seen.
Oh, first need to laugh.
Yeah, let x and y be real numbers such that x is less than y. Now, let's say in high level, really quick, high level language, what our axioms with inequality say. First one tells us if x is less than y, then it is not the case that y is less than x. Second one tells us less than is transitive. Third one tells us two numbers aren't equal, one must be less than the other.
Mm-hmm.
Next one says if y is less than z, then we can add the same thing to both sides of the inequality, and it doesn't change the inequality.
Might be the one you want to use.
That is the one we want to use.
That is the one we want to use.
And then the last one is, if y is less than z, we can multiply both sides of the inequality by a number greater than 0, and it doesn't change it.
Okay. So I already assumed this, right?
Yep.
Okay.
So we know that x is less than y. What else do we know?
It's less than y implies. Do I want to use x?
You're going to use the fact that you can add the same number to both sides of the inequality, and it doesn't change it.
What number do I want to add?
Well, how do you want to change your inequality? You want to change it so that instead of x over here, you have a negative y
I
over
have a
here.
negative y, so just
So what would you need to add so that you're just left with negative y?
Negative 2y.
no.
What can I add to x so that when it's all said and done, I'm left with negative y?
This seems obvious.
Negative x and negative y?
I've got x, and I want to add something to it. We'll call it z, so that we're left with negative y. What do I want to add to x so that we're left with negative y?
Oh, just negative 1. Oh no, that's multiplying. Okay.
You want c to be negative x and negative y, right? You do it
No,
twice.
what he's ultimately saying is I want this to be negative y.
No, you want your left-hand side to be negative y. X plus what gives you negative y? That what, you need to add to both sides.
It's the fraction.
You're overthinking this.
I am overthinking this. I just need to look at what you have written.
X plus something equals negative y. What is the something?
X.
Subtract x from both sides.
But then you're just left with 0.
You have the z. You're solving for z.
If z is equal
Why
to
do I want that? Sorry.
negative,
I'm confused.
okay. If z is equal to negative y negative x,
Okay.
then what is x plus y, or what does x plus z equal?
Just negative 1.
Just negative y. So if I add this to x, I'm left with negative y.
Okay.
What happens if I add this to y?
Then you have negative 2y minus, oh, add, sorry. Then you just have negative x.
Okay.
Look at what you're trying to get to.
Oh, so you just wrote it out for me. Right? That implies x plus. Now I want to substitute a z.
Tricky.
We need to find something to add to x, so that when it's all said and done, on the left-hand side of our inequality, we want just negative y. And whatever we added to get just negative y, better on our right-hand side, just leave us with negative
Okay,
x.
that's easy.
Okay.
Okay. Okay. That was way more simple than I made it. Right?
Those minuses or timeses? Or negative?
They're minuses.
X minus y minus z is less than.
So this equals 0, this equals 0, you're left with this and this.
Good?
Yeah.
Alright. Let's prove the next one. Next one's a quick corollary. We want to prove that for all x.
Isn't the corollary?
Is it 0 less than x?
Yeah, 0 less than x. In essence,
If x is a positive number, then negative x is a negative number. If x is greater than 0, negative x is less than 0.
Basically switching to 0 for y. Right? Basically, kind
the two
Basically.
arrows together, Donnie, means that you assume one, prove that's true, and then you assume the other and prove that it's true, right?
Oh.
of. If and only if.
Yeah, it's an if and only if. Sorry, that's what I meant.
I think both of these were supposed to be if and only ifs.
Well, then you just do the opposite.
Yeah. So going from here to here, what would we do? We'd start with this, and we'd add x and y to both sides.
Yeah.
And that would give us this. Okay. So now we're doing this one if and only if. So that's a back and forth arrow. We need to show that if this is the case, then this is the case. And then we need to show that if this is the case, this is the case. So it's like we have two little proofs to do.
Okay. Okay, so, alright, so I break this up into two different proofs, is what you're saying.
Sure.
And so, that's the case and this is the case, okay. Let x just in
X and R.
R. There's no such that.
There is going to be such that
Oh,
0 is
such
less
that.
than x.
Yeah. Now, if I add negative x to both sides,
x plus 0 is less than negative x plus x.
Well, which then just makes it negative x is less than x, or 0.
There you go.
So that proves that, and it's like the same exact thing. Well,
Going the other way.
okay, so let's just do that.
So if you would have instead known that negative x was less than 0,
I kind of just want to do a plus x both sides, so,
Yep.
okay.
perfect.
Okay, that was easy.
All right, next one,
You have the definition,
a
right?
definition. Simple definition. When we say that x is not less than y, that means that it is not the case that x is less than y. We usually have this line the other way. So, with that definition, we're now going to prove our next theorem. What number is it?
17.
Theorem 17. We're going to prove that for all x, x is not less than itself.
How would you go about proving something like that?
You assume by way of contradiction.
Okay.
I think.
That's one way to do it. The other way to do it would be to use the rule of excluded middle directly. Either it is the case or it isn't.
Oh, yeah. Well, isn't that basically the same as doing a proof by contradiction?
Exactly. So let x be an even real number. Assume by way of contradiction that x is less than x. All right, then what do we know?
Would you just use
Isn't there an axiom that is supposed to be useful here? Is it 10?
I don't know. Does that help?
Well, let me think. I think so.
Yeah,
I think so too.
I think so too.
makes sense to me.
Then it is not the case that x is less than x.
Contradiction.
Oopsie. Okay. All right.
I actually don't understand, what does not a number, what is that, not a number?
Not a
Not,
number?
not x, what is that, not x, technically?
It doesn't make sense to say not x.
So what's it say?
Oh, okay. So not can only be applied to things, booleans. It can only be applied to things that are true or false.
That's right.
So what it's saying is that if x is less than y, that implies not y is less than x. The not applies like that.
Oh. Okay, and that makes way more sense, okay.
Yeah.
He's the leader model.
Who?
Good question.
The leader model.
Who closed it on him?
Probably agreed it.
Oh, he. Here, Levi can call him.
All right. Let's see the next one.
Do you want me to tell him over or tell him?
Just ask him what he would prefer. If he can come over, that'd be awesome, but if we need to go grab it, then we need to do it.
The next one is just a lemma. We won't bother proving this one. It's almost identical to
It's
what Harley
identical to
proved.
what he did, yeah.
Just ever so slightly different, so we won't prove it. And we'll skip straight to 18. For all x, y, and z,
Okay, I'm gonna go grab the keys.
Okay. Let me know if you need me to come show me.
Okay, are we going to need to be with Aaron?
He's here, so I don't know.
theorem
You want to ask him?
18. All x, y, and z. We are proving that if x is less than 0 and y is less than z. So we're going to prove that if x is less than 0 and y is less than z, then when we multiply both sides of this by x, it flips the inequality. So then z times x is less than y times x. Let's give a concrete example of that. I know that 2 is less than 3, so that's my y and my z. 2 is less than 3. Now pick a number less than 0, we'll say negative 5. And we're saying if we multiply both sides by negative 5, it's going to flip the inequality. It's going to be that negative 5 times 2 is greater than negative 5 times 3. Or the way we have it written here, we instead switch which side we wrote on. So we're saying 3 times negative 5 is less than 2 times negative 5. Make sense?
Yep. Yeah.
Okay,
Who's it my go?
I think it's your go. Peter bailed on you.
Oh boy. Okay.
So we'll start by assuming the antecedent. Let x, y, and z be real numbers such that x is less than 0 and y is less than z.
Notice you put the R like that, so let me put that a little different.
That's just my lazy handwriting.
I kind of like it, because just doing a line and an R doesn't add up. So having it go across like that, I don't know.
Do an R and then slash.
Jeez Louise, I can't even do it now.
Yeah.
Okay. Oh, or just an R and slash in the middle. Okay. Okay. And such that x is less than 0.
And
And I can't remember and. Okay. And y is less than z.
perfect.
Okay.
Now, we know that we can multiply both sides of the inequality by a number, as long as the number we multiply is greater than 0.
Right. Okay. You're right. Without switching the symbol. What'd you call it? What term you referred to? Switching this. What was the term for that? Operator? No. But anyways. Okay.
So if we had a number greater than 0, we can multiply both sides by that number. We have a number x less than 0.
Is that saying? Okay. Right. So I understand that we're adding. We're adding a negative.
I need to find a number greater than 0, and then multiply both sides of this inequality by that number.
How will that run?
Well, it's the only way we can, it's the way we're going to have to manipulate it.
Hello?
Well, I get the x is that. I get.
No, x is less than 0.
Oh.
We need a number greater than 0.
Do I come up with another symbol in this circumstance?
Well, do you know a number greater than 0?
I don't know if it opens many doors, but I can ask.
1? I don't know.
You look at the information you have.
Okay.
You know
Okay.
that X, Y, and Z are all numbers.
Yeah.
And you're given two pieces of information. You know whatever X is, it's less than 0. And you know whatever Y is, it's less than Z.
Does your key open all the doors, Tom?
No.
Just this one?
This one.
We've been locked out, and I don't know how to get a key.
Okay, I know.
So we're looking for a number greater than 0.
Okay, wait a second. So this is saying x, z times some, a negative number. Oh, right, and this is accurate, and that it would be negative. You're saying we're looking for a number greater than 0. I don't understand what that means.
I know that ultimately I'm going to have to multiply both sides of this inequality by something.
Okay,
I need to do that.
right.
This is the only rule I have for multiplying both sides of an inequality by something.
Oh.
And it says we can only multiply both sides of an inequality by a number greater than 0. If x is greater than 0, then we can multiply both sides of the inequality by it. I don't have a number greater than 0. I have a number less than 0.
Right.
I wish I had a number greater than 0.
Should I make up a number that's greater than 0?
This is your only given information. Using this information, you have to find a number greater than 0. Imagine you're writing a function, and I give you 3 terms. I give you x, y, and z. I know x is less than 0. I know y is less than z. I tell you, you have to have your function return me a positive number.
Well, I know,
How would you do it?
Frick. I guess I would know that y or z is greater than 0.
Maybe both those are negative numbers.
Frick, maybe they are.
Maybe that's -2 and that's -3. If I give you let's just focus on the x. If I give you an x, and you know it's less than 0, and I say, now, make your function spit out a positive number, what would you do?
Times both sides by -1.
Just multiply it by -1.
Shit. Okay, so I was getting there.
Yeah.
Okay.
Take the number less than 0. So if x is less than 0, then negative x is,
Greater than 0.
then negative x is greater than 0.
Okay, cool. All
And
right.
that was using our little lemma here. So we didn't bother proving this, but if x is less than 0, that's the same thing as 0 is less than negative x. Or in other words, negative x is greater than 0.
Yes.
And so negative x, we know, is a positive number. We've got to be careful. We don't have this symbol.
Oh, so
We only have this symbol.
Are we trying to prove? But we're not defining it either.
We're not defining it. So, you know from this lemma that since x is less than 0,
Yes.
now you know that 0 is less than negative x.
Oh, okay. So what I could have done is just said, okay, so negative x times x is less than 0 is what I have, right? Is equal to
You
0.
have x is less than 0.
I do have that, and I could say it's equal to -1 times x is less than 0. And
No.
Oh, sorry, no. It's equal to negative x times x is, no, frick. Okay, it's 0 is less than x times -1.
Okay, you can do that, but it's not equals, it's logically equivalent.
Thank you.
Okay, so those say the same thing. That was using our lemma.
Yes.
So I know that if x is less than 0, then x times -1, I guess.
0 is less, or sorry, x, yeah, you're right.
This is now greater than 0.
Right.
So this is a positive number.
Mhm.
And what does my axiom say? My axiom says if y is less than z, I can multiply both sides by a number greater than 0,
Which is this one.
which is that number. So now I can take y less than z and multiply both sides by this number.
Good point. Okay.
Okay.
So I know
So
that.
now we're getting somewhere.
And okay, I can take that. And this I can say that is, if this is the case, then this is no, I can't see that. If this is not the case, then this is the case.
It turns out you can go from here.
To there.
Well, we better be careful with that. But this one does say that we can add the same thing to both sides. So far, let me just write what you have, but just clean up a little bit.
I said add. It's add.
No,
Oh.
this is multiplied. You're good so
Okay.
far. We have two things we can do to an inequality. We can add the same number to both sides, or we can multiply both sides by a number as long as that number is greater than 0. So far, you multiplied both sides by a number that we knew was greater than 0.
Yes.
Okay, so rewriting what you have here, you have negative x times y is less than negative x times z. Or sorry, let's change the order there. You have negative y times x is less than negative z times x. That's what you have so far,
You're right.
right?
Yep.
You're trying to get here. You're
Right.
trying to show that z times x is less than y times x.
Okay. And so that was just a simplification, essentially.
Yeah, I was just rewriting it a little bit cleaner so that you could see.
Right. I tried to be explicit because we're working with symbols and stuff, but that I understand how you did that.
Okay.
Okay. Oh, so I could times both sides by negative x, and that would give me, no, it's not what I want. Or times it by negative 1. Okay, I'm trying to get this. This is what I have. This is saying y, negative y times x is less than negative z times x. And this, okay, so I would need to times it by, yeah, negative 1. Yeah?
We don't know that we can do that.
We can't times both by negative 1? We don't know. if
We
can
only
do that?
know that we can multiply both sides by a positive number. We can multiply both sides by a positive number, or we can add the same thing to both sides. We know those. The other thing we know are the theorems we already proved.
Right. Oh, okay. So using theorem 16,
There you go.
thank you, that y times x is less, is,
Other way, you flip them.
flip them, yeah, right, okay. Just want to make sure. No.
It's saying
Oh,
you can
yeah,
get
yeah,
rid
yeah,
of the
yeah,
negative
yeah,
signs
yeah.
if you swap the symbols.
That's correct. Swap the symbols, we have the x is less than yx.
Now what?
That's literally it.
That's it, we're done.
Okay,
Okay,
so that proves it.
that proves it.
Great. Is there
So we
anything else I need to-
multiply both sides by negative x. All we did is multiply both sides by negative x, because that was a positive number. So we started with this, we multiply both sides by negative x, which was a positive number. And then we use theorem 16, which says, now to get rid of your negatives, flip the sides.
That's right.
Those were the two pieces of logic we used. Okay. All right. And that pretty much concludes our dive into arithmetic. Maybe say a little bit about dividing by 0 as an off point. So we say that you can't divide by 0. And often students want to know, why can't you divide by 0? So they have a lot of answers to what they think it should be. 2 divided by 0, what could we possibly guess that should be? What does it make sense to call it?
It would make sense if it was 0, I guess.
You might think it's 0. Okay. But now let's look at definition for what this means. If 2 divided by 0 equals 0, that would be logically equivalent to 2 is equal to 0 times 0.
Right.
And 0 times 0 we know is
That's 0.
0. In fact, for any x, if I took any number, I say I want that number divided by 0 to just be 0, then we would get that 2, or then we would get that x is equal to 0 times 0. But we know that 0 times 0 is always and forever 0.
It's infuriating that there's just one situation that's undefined.
So it seems to be given this grief here. What else might we think x divided by 0 could be? If we try and get some intuition for how division works, when I say, what's 20 divided by 4? We say that's 5, because 4 goes into 20 5 times. So if I break my 20 up into pieces of 4, I may have 5 pieces. If I break 20 up into pieces of 1, I may have 20 pieces. If I break 20 up into pieces of a half, I may have 40 pieces. And so if I break 20 up into smaller and smaller pieces, I get more and more pieces.
Gets closer to infinity.
Yeah. So maybe we want x divided by 0 to be infinity. Maybe that's a natural answer for it.
So it could be 0, it could be infinity.
Well, we showed saying it's 0 doesn't make any sense.
Yeah, thank you.
So we've already gone down the path of maybe dividing by 0 should be 0. No, that doesn't make sense. Because then I get 0 times 0 is equal to anything. 2 is one example of what we got. Which doesn't make sense. Because we already proved as a theorem, anything times 0 is 0.
Right.
So we know 0 times 0 is 0. We're getting 0 times 0 equals 2. That would mean 2 is equal to 0. But we already know 2 is not equal to 0. So that would give us a contradiction. So it can't be 0, maybe infinity. Maybe that works. Well, a couple of problems here. First problem, so let's pick a concrete number here. We're saying 2 divided by 0 equals infinity. That would be logically equivalent to 2 is equal to infinity times 0, right?
So it's still not correct.
Well, I don't know, maybe that could somehow make sense. But then 3 divided by 0, we also want to say, well, that's also infinity. So then 3 is equal to infinity times 0. And so 3 is equal to 2.
Right.
And so that breaks it. So we can't really say infinity. Furthermore, infinity is not a real number. Infinity is not a number.
Is there a definition for infinity?
No, it's not. I mean, there are systems set up where infinity is a real number. Is a number, sorry. So if we talk about what we call the extended reals, which has its own axioms, then yes, infinity is a member of the extended
Would it be
reals.
considered like a primitive?
We won't worry about it. The point is, infinity is not a real number. Because which real number would it be? You want to say it's the biggest real number. But we can do a trivial proof that there is no biggest real number.
Because you can always add 1.
Because you can always add 1. Assume by way of contradiction that x is the biggest number. Well, consider the fact that x plus 1 is greater than x. So we found a bigger number. So there is no biggest number. So we can't define the biggest number to be infinity. If there were a biggest number, then sure we could call that thing infinity and go from there. So 2 objections to this. One objection is we're getting 2 equals 3. So we can't really call anything divided by 0 infinity. That runs into a problem. So we couldn't call it 0, we couldn't call it infinity. What should we do when we divide by 0?
Call it 1.
Call it 1.
Call it 1, of course. 2 divided by 0 is equal to 1. Because that's logically equivalent to 2 is equal to 1 times 0.
Oh.
Okay, that doesn't work. Doesn't matter what you try to call it. 2 divided by 0, if we try to call anything, let's just call it x. Let's not call it anything yet.
We don't know what it is yet, but it is there.
But let's pretend that there is something that makes sense for it.
Right.
Well, what would that mean? That would mean 2 is equal to 0 times x.
Yeah.
But we know 0 times x is always and forever
0.
0. So there can't be an x that you plug in there. Right?
And why was it not 0?
Because of an axiom. Right?
Why is it not equal to 0?
Yeah.
Same problem. What's 0 times 0? 2.
Oh. Okay.
Okay. So we can't do
So
0.
much.
We can't do 2.
It's like a black hole.
Now, someone out there might say, okay, fine. We can't do any number divided by 0, but surely we can define 0 divided by 0. And that should just be 1. Right? At the very least, this should work.
Oh, okay.
Right?
Yeah.
And let's check it. That's logically equivalent to 0 is equal to 1 times 0. Is that true?
No.
That is true.
That is true.
But it could be true for all numbers.
Doesn't matter. So 0 divided by 0 is equal to any number you want.
So we got it equal to 1. It doesn't break over here at least. He's reverse engineering. He's saying you plug in any x over here and that's true. Therefore, you can have 0 divided by 0 is equal to anything.
Yeah.
That's a great objection. I'm going to give that same objection in a more pictorial way.
Well, you could just do 0 divided by 0 is equal to 1. 0 divided by 0 is equal to 2. 1 is equal to 2.
Right, same problem. You can make it equal anything. So you can make anything equal to anything
Yeah.
else. So that is a good objection. I'm going to give you a pictorial way of seeing this. One that you probably have never thought about before. Same logic though. We're jumping ahead to going to talk about real number lines
Okay.
and graphs of lines. So right here is going to be the graph of the line y is equal to x. What's the slope of that line? 1. Right? Just y equals x. And let's talk about a random point on here. If we go to 4 right here as an input, what's its output going to be? 4. And so this is a line with slope 1. This is a line divided both sides by x. This is a line where everywhere on the line y divided by x is equal to 1. You plug in 4. 4 over 4 equals 1. You plug in 1. 1 over 1 equals 1. It goes through the origin. 0.
0 over 0 is equal to 1.
So then you get 0 over 0 equals 1. Right?
Yeah.
Okay.
But now let me pick a different line. Oh, let's look at this line. Y equals negative x.
Oh, I see where you're going.
Divide both sides by x, and you get, on this line, y over x is always equal to negative 1. The slope everywhere on this line is negative 1. So if we go over here to negative 4, it goes up to 4, and we get negative 4 over 4, negative 1. Or we go over here to negative 1. Negative 1 over 1 is equal to negative 1. We come down over here. 4 over negative 4 is equal to negative 1. Everywhere it's negative 1. What about the origin? It goes through the origin. And we get 0 over 0 equals negative 1. And if we define it, I can make it equal to any number you want. I just pick the line with that slope that goes through the origin.
Yeah.
I hate this so much.
So,
But it,
exact same argument for, if you define 0 divided by 0 to be anything, you can make it equal to everything. If you allow it to be defined.
same logic.
Same logic.
Yeah, that's not.
Just a pictorial one that maybe you have never thought about before.
That's if you define the line that way. I mean, what I'm saying is it makes more sense to define your line by y equals x than it does to divine it by y divided by x equals 1.
This is just deriving it from that.
Yeah, but
Because it's valid to always do this if division by 0 makes sense for the whole line.
But if you make that step, then you all of a sudden have to restrict your domain. Because you would say you can no longer use 0.
Right. I'm saying if
What
we
I'm saying is you
could.
would never actually do that because you'd have to restrict your domain.
Right. I'm saying if we did allow division by 0, this is now a valid step.
Yeah, yeah,
Yeah, okay. So if you allow division by 0, we can make it equal to anything.
yeah.
Come to think of it, if the line hits the x as 0 in any location, it becomes undefined.
Only if you have a
If
visual.
the
So
line-
anytime that a line crosses the y-axis, it's undefined. Because x is 0, and it's y divided by x.
No. Has to go through the origin. For example, let's do y is equal to x plus 1. That's this line.
Oh, okay, never mind. Yep,
Doesn't go through
you're right.
origin.
Thanks. Okay.
Okay. Alright, so that was about 0 divided by 0. Let's do a little bit more with zeros while we're here. What about like 0 to the x? What does 0 to the x equal? Well, let's think about 0 squared. What's 0 squared?
0 times
0 times 0.
So 0.
So 0. What about 0 cubed?
0.
0. 0 to the 1/2. What's the square root of 0? 0. So 0 to the x is always just going to be 0, right?
That makes sense.
It makes sense. What about 0 to the negative 1?
Which is 0 divided by
Supposedly that
0.
should be 0. If we're going
That's
up
asking
and down.
for the multiplicative inverse of 0.
Doesn't exist.
Doesn't exist.
Because you have to get something that times 0 that equals 1.
Oh, but nothing times 0 equals 1.
So
Right.
zero's
0
only
doesn't
defined-
have-
This would only be defined when x is positive.
This is only defined when x is positive.
Okay.
If x is a negative number, this is no longer defined. Similarly, 0 to the 0. Well, let's look at another one. So 0 to the x, that's 0 anytime x is positive. Let's look at another one. Let's look at x to the 0. What does this equal?
1, right?
1 for any x, right? And that one works for both negatives and positives.
So 0 to the power of 0 is 1.
So 0 to the 0, what is it?
It's undefined.
Yeah, it's
Do we,
both.
is it 0 or is it 1? What is it?
It's synonymous. You want us to pick one?
Yeah, what do you like more?
1.
You like 1?
Yeah.
So if you take 0 0 times, you get 1.
Multiply 0 by itself 0 times and you get 1.
It's actually a pretty good intuition because the empty product is 1. 0
Yeah.
factorial, for example, is equal to 1.
That's true.
So think about it that way. That's actually a pretty good intuition. A pretty good argument for 1. And sometimes they will say 1, sometimes they'll say undefined.
I like your little complex number thing about that. I hadn't thought of that before. Because
Yeah.
it makes sense if you don't consider complex numbers.
And the way that we can show this is undefined is using complex numbers. We take the limit as x to the x approaches 0. We take the limit as x approaches 0 of x to the x. And we can get two different answers when we do it over the complex numbers.
Right.
Some people like to call us 1 because when you only consider it coming from the left and coming from the right on the real numbers, you just get 1. And so it seems like it's a pretty good number, a pretty good answer to it, if you ignore some stuff.
Can we go
But
over
approaching
that
it from the
limit?
left introduces complex numbers, so there's a
Can
problem.
we go over that limit as x approaches 0?
Can we go over it? I
Yeah.
mean, we can't do calculus. No.
Oh, I mean,
That's what we do.
0 to the x. Oh, there you go. Okay, I see.
Okay. So that was dividing by 0, and trying to give you some good intuition and some good explanation for why dividing by 0 is undefined. I'm debating. Should we start theory of definition?
Did we do all of the proofs we were going to do?
We did all the proofs we were going to do.
Oh.
Mostly just problems today.
Why do you? Oh.
What do you guys think? Should we start theory of definition or should we call it there?
My vote is call it because Levi and I need to go help Aaron for a bit.
Okay. We can call it.
It's too bad because I was excited to get it